Welcome back, students. Today we're going to be talking about function notation. So function notation is what you're seeing on your screen right here. It's this f of x that's written right here. Now this is not f times x. Notice the pronunciation that I used. This is f of x. Now these parentheses around the x are to identify what the input of this function is. So the input of the function is going to be x. The name of the function is f. Now a common mistake students will make is thinking that these are being multiplied. These are not. This is a new way of writing it, that is to say that the output f given whatever this input is equal to this. Now over here it's identifying what is going to happen to the input in order to get the output. So whatever x is, whatever the input is, we multiply it by 2, and then we subtract a 7. Okay, so let's take a look at what that looks like when we're evaluating. So I've written out my function, f of x equals 2x minus 7. Now we wanted to evaluate this when x is a 4. So I'm going to change my x everywhere to a 4. Now over here, this says that the function f, when the input of 4 is equal to 2 times 4 minus 7. Now I am done evaluating the left side. There's nothing more that needs to be done here. Over here is where a lot of our work is going to happen. So now I can follow PEMDAS. I'm going to do my multiplication before I do that subtraction. So now I've got f of 4 equals 8 minus 7. Now f of 4 equals 1. So the benefit of using this type of notation, there's a few, but what we'll talk about right now is that it puts the input and the output in a single line. So when the input is 4, the output is 1. Okay, so let's try it again. This time we'll evaluate it when x is a negative 4. When it tells you what the x is, replace x with that variable. So now rather than focusing in on the input of x, we're focusing in on the input of negative 4. We pronounce this by saying this is f of negative 4 is equal to 2 times negative 4 minus 7. So f of negative 4 equals negative 8 minus 7. F of negative 4 equals negative 15. Okay, and so now that I'm done evaluating, I can see that when the input is a negative 4, the output is a negative 15. And that's all you're going to be doing when they ask you to evaluate the function. Whatever you change the x to inside the parentheses is what you're going to change the x to in the right-hand side. Okay. Now let's talk about how to interpret it. Okay, all of mathematics exists to explain the real world. I shouldn't say all, but most of mathematics exists to explain the real world. And this is definitely no exception. This is a shorthand, a very quick way of writing something that is much larger. So here we've got this example where f of t represents the outside temperature in Fahrenheit. So F, which is our function, T is just the input, but F is the function. F is representing the outside temperature in Fahrenheit. T is representing the hours after 10 a.m. So we want to explain the meaning of various statements. So let's look at this first one. Now, in my head, I'm going to replace F with the word temperature because that's what it represented. So the temperature at, now T has changed to 0. T was hours after 10 a.m. So 0 hours after 10 a.m. means it's 10 a.m. So the temperature at 10 a.m. is 75 degrees. And that's how we interpret it. Now, this is one of the other benefits of using a function notation. When you are dealing with word problems, that very small statement actually is saying a lot, so long as we know how to decode it. Okay, next one. F of 3 equals N. So F was temperature. The temperature at now 3 hours after 10 a.m., that must be 1 p.m. So the temperature at 1 p.m. is or was N degrees. We don't know what that value is, but I can still write it like this. At 1 p.m., the outside temperature was N degrees. Now this one gets even more complex, but remember what I said about simply replacing each variable with the word that it represented. So F, temperature. So the temperature at 1 hour after 10 a.m., so 11 a.m. So the temperature at 11 a.m. is greater than the temperature 8 hours after 10 a.m., so 6 p.m. The temperature at 11 a.m. is warmer because it needed to be greater than, so if we're talking about temperature, warmer, than the temperature at 6 p.m. Okay, and that's how we can interpret these very small statements. These small statements are full sentences explaining relationships. So now we're going to solve for the independent variable. The independent variable is x. So here we've got our function, g of x equals 1/3 of x minus 2. We want to find what x value, find the value of x, that gives us g of x equals -4. So in other words, I want to know what input value x would give me an output value of -4. And that's what this final statement is saying, where the output, because that's what g is. G is our output. It's the function, where that equals -4. So let's set this up. We've got our equation. We've also been told we want to know when g of x equals -4. So let's go ahead and change g of x to -4. And now we can find what x value would make g of x equals -4 by solving for x. I've got this multiplying by 1/3 and then -2. I'm going to deal with the -2 first. We'll add 2 to both sides. So -2 plus 2 is 0. Anything plus 0 is still itself. -4 plus 2 is -2. Next step, I need to deal with that multiplying by 1/3. Okay, so if we were to flip that fraction upside down, it becomes a 3 over a 1. And so I'm going to multiply by the opposite fraction, or in other words, 3. Now what this causes us to have is 3 times 1/3, which would be 3/3. 3/3 is 1. 1 times x is just x. So we get x. 3 times -2 is -6. So what's the value of x that would give us g of x equals -4? It's -6. Okay, and we could quickly test that if we wanted to make sure. 1/3 of -6 should be a -2. -2 minus 2 would give us -4. So the input of -6 gives us the output of -4. And that's the process. If they give you an output number, just replace your function with that number and then solve for x, and you'll know what input would give that output. Graphing a linear function in function notation. So here's our function, f of x is equal to 3 minus x. We're going to make an input-output table to find the ordered pairs. If we're trying to graph it, then I want to know the x value, I want to know the y value. Well, it's clear which one is x, and in place of y, I'm just putting f of x. So 3 minus 0 was 3, 3 minus 1 was 2, 3 minus 2 is 1, 3 minus 3 was 0. So now I've got my x, y values, or my x, f of x values. Either way we say it, it's going to be graphed the same. So now we're going to plot these ordered pairs at 0, 3, then 1, 2. Okay, now 2, 1. Finally, 3, 0. Final step is we can see that clearly forms a line. I'm going to draw a line straight through it. All right, now modeling with mathematics. The graph shows the number of miles a helicopter is from its destination X hours after flight. So to make this clear, let's just look at it. We can see that at 0 hours into the flight, they were 300 miles away. After 1 hour into the flight, they were then 200 miles away. And that's just how we quickly read the first flight's graph. On its second flight, the helicopter travels 50 miles farther, but it increases its speed by 25 miles per hour. So then we get this function. Now notice this 350. It said we went 50 miles farther. This had been 300. Well, 50 miles farther than that. And we are decreasing our distance by about 125 miles per hour. This is going to be 25 miles per hour faster than what the first flight did. Okay, so this function right here is going to represent the second flight, where f of x is the number of miles and x is the number of hours. So which flight is going to take less time? Well, I can look at the first flight right now and see exactly how long it took. It took it 3 hours to get 0 miles away. That's when it reached its destination, in 3 hours. So if we could graph this function, we would be able to also see when it finished by just seeing when it finally reached 0. So we're going to make a table. We've got these values, 0, 1, 2, 3, and all I did here is I put these numbers into this function. So when x was a 0, 350 minus 125 times 0 was 350. When the hours was 1, 350 minus 125 times by 1 is 225. So let's start graphing those points. 350, 1, 225, 2, 100. The next one has a negative, so it would be off. We're going to draw a line through that, and notice it ended before 3 hours. And that's why at 3, it was at negative 25. The helicopter would have stopped, but we're assuming if it kept on going in this, it now would have gone 25 miles past its distance at 3 hours. Okay, so it looks like the second flight took less time. Now, let's just make sure that we're right in that. And let's check our answer here. So we've got 0 is equal to, we want to know when it reached 0. So this is similar to the problem where we were solving for the independent variable. What we're also going to get out of this is we're going to figure out how many hours exactly did it take. Because looking at my graph, it's not 100% clear. I could estimate it, but I'm not sure. So now we're going to solve for x, minus 350 from both sides. And then we get negative 350 is equal to negative 125x. We're multiplying x by negative 125, so we'll divide by a negative 125. So x equals 2.8. So it took it 2.8 hours to finish. That once again confirms exactly what we saw from the graph, that the second flight was going to take less time. I hope this helped you. Good luck.